so much for coming. We hope you enjoy Jarryd's talk. This is Jarryd Bath. He's going to be talking about supersymmetry. When the talk is finished, there are some thank you notes and CTs that anyone can help them talk to at the end. I hope you enjoy the talk. Thank you.
Hey guys, so as Natalie just said, I'm Jarryd Bath. So I am currently a master's student in the high energy theory group, supervised by Professor Zubels. My research interests are in supersymmetric field theories, superconformal field theories, and quantum field theory, ADS-CFT correspondence. So I really like supersymmetry. First time I was formally introduced to it was during a string theory school in 2022 by Dr. Sam van Leuven from WITS, and so he kind of inspired me to give a similar presentation, so I have to give him his dues, and I'm actually collaborating with him on a project. So yeah. So first, before I even begin off, let's before I throw words like bosons and fermions around and so we consider a particle system. We have two identical particles, which are labeled by 1 and 2. And the oval state we denote by K12 K112, and since these particles are truly identical, quantum mechanics tells us that swapping the states, so particle 1 now is in state 2 and particle 2 is in state 1, we haven't changed the physics of our system. So any physical experiment that we can do shouldn't be changed by the swap. And what we measure are probabilities, right? So the most that we can get is a phase when we do the swap. So as I denoted psi, and as I said, it's a phase, so its norm is 1 to preserve the inner products. So now we can swap these states again, and because these are truly identical, we get the same phase back. So now we're left with psi is equal to psi squared psi. And this gives us that psi is equal to plus or minus 1. So the states that are symmetric under the exchange of states with psi equal to 1s are called bosons and obey Bose-Einstein statistics. And particles that are antisymmetric under the exchange of states are said to obey Fermi-Dirac statistics. And notice if we have two particles that are in the exact same state, that would give us 0. So if we had a state 1, 1, which is simply Pauli's exclusion principle. So why supersymmetry, or what is supersymmetry rather? So as I said, we can classify particles by their statistics. And we also know from great minds like Newton, Einstein, Gell-Mann, and many others that symmetries are the underlying principles of physics. And so we have two ingredients, symmetries and statistics. So it's only natural for us to try to come up with a recipe that combines these two. And the cake that we end up baking is called supersymmetry, or SUSY. So that is, supersymmetry is a symmetry between the bosonic and fermionic degrees of freedom of a system. So I just want to introduce some conventions. And so, yeah, as I say, I'm a high energy theorist, and I get scared by weird symbols and numbers. So we work in natural units where C, the reduced Planck constant, and the Boltzmann's constants all set to 1. To restore these factors to actually compare to experiments, we can do via dimensional analysis. So in these units, we have time have the same dimension as length, momentum and temperature have the same units as energy, and length and energy are inverses of each other. And I won't be using any hats to the net operators because I'm kind of lazy. And we not a convention, but the main focus will be working in canonical quantization. So that is, we upgrade observables to operators and apply the Dirac quantization condition, which is to take the Poisson brackets of classical mechanics and they become commutators, or 1 over I times commutator. Note that throughout I will be using curly brackets. Otherwise, these will be anti-commutators and should not be confused with these Poisson brackets. So why do you actually study SUSY? So first is strongly coupled systems. So our knowledge of these are actually very broad. The main technique that we use of perturbation theory in anything with a strongly coupled system fails, because the idea of perturbation theory is to expand in a small parameter, which is the coupling. And when the coupling is large, that kind of Taylor expansion fails. So things like QCD, or the study of the strong force, being strongly coupled, as the name implies, means large coupling. This is actually extremely limited. And supersymmetry actually makes exact predictions regardless of the value of the coupling. So, for instance, there is a model by Witten and Seiberg, n equals 2 theory, that actually shows the phase transfer from confinement to deconfinement that one has in QCD. So we have toy models of the real world. We can play with these and understand the world better. And the next is phenomenological reasons. So spontaneous symmetry breaking is the best current solution to the hierarchy problem. And the hierarchy problem is that the Higgs mass is way too small. So you may say it looks very large there in the top right corner at 125 GeV. The only fundamental particle with a greater mass being the top quark. Well, studying QFTs, you know that a scalar particle, which the Higgs boson is, should actually be running, the mass should actually go towards the cutoff of the theory, which is, usually taken to be the Planck mass, which is, I think, 10 to the 19 GeV compared to 125. So clearly something is going wrong, and QFTs has been really good at predictions, so there must be something other that we're missing. And it turns out in supersymmetry, supersymmetric theories, the contributions to the mass of a particle, of a scalar particle, actually cancel. You don't get any corrections. So if one were to slightly break that supersymmetry, then you would end up being able to just get a smaller contribution to the mass. And so obviously we don't see any of these supersymmetric particles. You would expect to see, a massless fermion corresponding to the photon, which, being creative namers that we are in physicists, would be called a photino, and you don't see a massive boson corresponding to the electron, which would be called the selectron. Additionally, if you are a believer, other people would put it into the maths category. Supersymmetry is required for consistent string theory. Also, if anybody has any questions, you can interrupt me. So without supersymmetry, it seems, yeah? Without supersymmetry, it turns out that the vacuum of string theory, bosonic string theory, is unstable. You have a negative mass squared for it. So that tells us it sits at a maximum of a potential. And so the only way so far I believe, is via supersymmetry to correct that. So, and as I said, mathematics. So as one studies supersymmetry more, you get to more sophisticated math concepts. So these are often focused on index theorems. So Morse theory, even we've even found through a study of a two-dimensional supersymmetric field theory, we've discovered mirror symmetry that wasn't known before the study, a physics paper, which will relate to topologically distinct manifolds. And in 4 dimensions, which we live in, the study of chiral models are actually very closely associated to the study of Kähler geometries. And we obviously, in addition to these very geometric perspectives, it plays a huge role in my work with the ADS-CFT conjecture. And then finally, I find it very neat. That's why I study it, so I hope you guys also do. So, supersymmetric quantum mechanics. So, it's the name that we give to a class of Hamiltonians that can be written. So, yeah, this operator Q for the supercharge squares to 0. And so this operator actually behaves somewhat like the square root of a Hamiltonian. So that equation 7 is called the supersymmetric algebra. And it actually just fully describes supersymmetric quantum mechanics. Thanks, guys. Actually, as you can see, I have many more slides. So now we can actually look at the properties that result from the supersymmetric algebra. So the first thing that we can see is that the energy spectrum is always necessarily non-negative. So if we have a Hilbert space, the curly H, and we have the Hamiltonian H acting on some state psi in the Hilbert space, then we can consider the expectation value of H on psi. And if you'll notice in the first line, of 8, we actually are considering 2. And as we know, for them, this we have to have that these are always greater than or equal to 0. We're summing 2 quantities that are greater than or equal to 0. The overall sum must be greater than or equal to 0. So the energy eigenvalues are therefore greater than or equal to 0. And the energy is going to only be 0 for states that are annihilated by Q and Q dagger. So it has to be annihilated by both. Now, we should be a bit, perturbed by the fact that we have a positive definite energy spectrum. Since in physics throughout classical and even regular quantum mechanics, we can always add a constant to our potential and change the overall energy and leave, the physics unchanged. For instance, the forces between these 2 potentials that are related by constant are still the same. So it's the same system. And in the quantum setting, we'll see that any eigenstate of one Hamiltonian that is being shifted by constant, the eigenstate should be shared by both Hamiltonians. And all we've done is actually just shift our energy, the energy spectrum. So while this shouldn't be surprising because we measure energy differences in physics, we should be oblivious to the overall ground state. So it seems that kind of breaks down in supersymmetry. We actually, we can not just lower the energy below 0 and keep supersymmetry alive. There's actually one other place in physics that we've seen the overall ground state energy where it actually matters. So if you look at Einstein's equations, the capital G over there is Einstein's tensor, and the capital T on the far right is the stress energy tensor, which tells us that there's matter or in the space time. And so if there's no matter, the right-hand side is 0, and we're left off with this lambda times the metric, the lowercase g. And so what you can think of, that lambda is called the cosmological constant, and somewhat thought of like the ground state energy of, or vacuum energy, and actually will determine the overall curvature of the universe. So unfortunately, there are no found links between the two, supersymmetry and the cosmological constant. But also now we have that our positivity of the energy can rule out several systems immediately. So the hydrogen atom, for example, has a negative energy spectrum. So that we can discard it. So we always have a positive definite potential when we consider supersymmetric theories. So with symmetries in quantum mechanics, one gets a degeneracy. So we have multiple states that have the same linearly independent states with the same energy eigenvalues. So I'm leaving it as an exercise, but you can show that H and Q commute just from the fact that Q squared is equal to 0, and we know the form of H. So if we have an energy eigenstate, then we know that both Q and Q dagger acting on that state will still be eigenstates. So first we can consider the non-zero energy states. And we can find an operator C, which is as denoted in 15, and we can study its algebra. And we get that the anticommutator of C and its dagger is just 1. And if one looks back to the harmonic oscillator, this is simply the algebra while swapping the anticommutator with commutators of the raising and lowering operators, which are usually called creation and annihilation operators. So these are fermionic creation and annihilation operators. So we can essentially write the vector space spanned by, so this algebra has a two-dimensional irreducible representation that's spanned by two states, which we call 0 and 1. And these, we have that 0 is annihilated by C, and C dagger raises 0 to 1. And which is equivalent to saying C dagger annihilates 1 and C lowers 1 to 0. So the algebra says that all the energy states with E not equal to 0 comes in pairs. So we also could have further degeneracies through things like rotational invariance. But at each level, energy level, there will always be an even number of states with the same energy. So now we can look at the ground states if we have energy equals to 0. If, as we say, they're ground states, so this argument highlighting degeneracy now fails. We cannot define those C's and the C daggers. And we know that these are necessarily annihilated. So there's a possibility that we can have a lone ground state, get omega, that will be annihilated by Q and Q dagger. There are, again, possibilities that other degeneracies may occur, but these are not going to be related by the actions of Q and Q dagger. So this can be formalized slightly. So we can define a fermionic number operator which if you look back to your, again, quantum harmonic oscillator, if you define a number operator in a similar way, it just will count the energy level that your particle is sitting at. And so F, the commutations of F with Q gives you -1 times Q. F with Q dagger gives you +1 times Q dagger, and F commutes with the Hamiltonian. So, as we said, this is only well defined with energy states not zero, and we now then give the fact that our states 0 and 1 are eigenstates of this fermionic number operator. So if we act on the state 0, we get, with F, we get 0 times the state 0. And acting on F, the state 1 gives us 1 times the state 1, hence the names 0 and 1. So the Hilbert space decomposes into the bosonic states with F equals to 0, so no fermions, and the fermionic states with F equals to 1. So we write those HB for the bosonic Hilbert space, and we have HF for the fermionic one. So this is called, this terminology is just called a Z2 grading of the Hilbert space. So either energy pairs that are not have energy not equal to 0 have one state in the bosonic Hilbert space and one state in the fermionic. And now, at the moment, we can't really say anything about the E equals 0 states. So this will be more clear as we go on, and will depend on the context. And I just want to introduce some terminology. If we have a ground state with E equals to 0, we say that supersymmetry is unbroken. And if we have a ground state with energy greater than 0, we say supersymmetry is broken. This is just adopted from QFT, where symmetries that that do not leave the vacuum invariant are said to be spontaneously broken. So just to kind of quickly get to why it's called, why annihilating a ground state is actually a symmetry, is that we have that the supercharges actually are what we call generators of a symmetry. So a symmetric transformation. So we can write this transformation as U to be that exponential in 21. And we know that Q and Q dagger both commute with the Hamiltonian, so that U will actually also commute with the Hamiltonian. And so that is how one describes a symmetric transformation of a system. So to actually get to something finally concrete, we now consider the quantum mechanics of a particle on a line, and we'll be considering it in a potential that we introduced just now. Our Hilbert space, the usual L2R, which is just the square renormalizable functions on the real line. That is, if you take the norm squared of a function and you can integrate from negative infinity to infinity, and you get a real number that's non-zero, then it will sit in that Hilbert space. The C2, C squared factor is just that internal degree of freedom that we said as 0 and 1, the fermionic number. So the C2 part is spanned by our states 0 and 1. And then we can kind of, I wouldn't say it's best notation, but it kind of, we can then decompose the Hilbert space as follows. We have the square renormalized functions times the 0 state, and plus the square renormalized functions times the 1 state. And just throughout, I'm going to just be setting the mass equal to 1. Again, I don't like scary numbers and symbols. Yeah?
So was that a direct sum?
Yeah, it's direct sum. Don't worry too much about that for now. It's just rotationally saying that we can split the Hilbert space into 2. It's me. So now we actually consider concretely what these Hamiltonians will look like. So if we let H be an arbitrary real function on R and obviously differentiable, and we have the regular momentum operator, and we can define our supercharge as the momentum minus I times the first derivative of that function times the matrix in 25. One could check because of the 2 by 2 matrix sitting there that Q squared is necessarily 0. And also we can just find the conjugate charge by conjugating Q itself. Now we can plug these supercharges directly into our supersymmetric algebra, and we find the following Hamiltonian given in 27. So notice that the first factor doesn't depend at all on the quantum number of the fermion quantum number, because we have an identity. So that's just the usual Hamiltonian associated to a particle on a line. Now there's an additional part which differentiates between the whether it's in a fermionic or bosonic Hilbert space, which is given by that sigma 3, which is just the usual Pauli matrix, which is diagonal of 1, on diagonal 1, and minus 1. I think I should have written that. Let me hide this, excuse me. And so our normal potential is given by 1/2 times the derivative of h squared, which, as you can see, is positive definite because h is a real function. Oh, yeah. There's the Pauli matrix. And as I said, it distinguishes between bosonic and fermionic particles by that relative minus sign. And one can check that the fermionic operator is simply given by the equation 30. And this now happily extends to the 0 energy states. So that gives us at least, now we can see how we can count the 0 energy states. And we can write the bosonic parts of the Hilbert space as a regular wave function times by the state 0, which we will just denote in kind of standard notation as 0, 1, column vector, and the fermionic part of the Hilbert space is spanned by also a regular wave function times 1, 0, column vector. So now the first thing is we can study the ground states of the system. So let's suppose that we actually have an energy E equals to 0 ground state. So we should be able to write it in as a linear combination of a fermionic and a bosonic part. So now we know that this, because it's E equals to 0, we have to be able, it's annihilated by the supercharges. And now we actually have a set of 2 linear equations that are decoupled. We started off with a second order differential equation from the Schrodinger equation. Now we've reduced it to 2 decoupled linear equations. So that's one of the first magic things that we've seen from Susie. It's going from something really challenging to something really quite simple. And as we can see in 35, we can find solutions to this equation straightforward, where we have an exponential of minus h and an exponential of h. So now we need to know which ones actually will be in our Hilbert space. So that actually depends on the function h. So just looking back, since we have a minus sign for the fermionic part and a plus sign for the bosonic part, we should just keep that in mind. So as if the h goes to infinity, as we go to the asymptotic in x, we know that our fermionic part will be normalizable, and the bosonic part will blow up to infinity. So we actually have to set that equal to 0. And we have a unique ground state that sits in the fermionic part of the Hilbert space. If the other case happens where we have h going to minus infinity, then phi is normalizable, and we have that the fermionic part will blow up. So we have to set that equal to 0, and again, we have now a bosonic unique ground state. So if neither of these properties hold for h, there's no E equals to 0 ground state, and supersymmetry is broken. And there will be a ground state still, but it will not have energy equal to 0. So we can start off with I say example 1, but I just have it as the only example at the moment. The cubic potential or cubic H just took too much time. So if you want to talk about that, it is quite interesting. Just come to me in 5:20 and we can have a discussion. So we take the potential given by omega, half omegas times x squared, and we take this to be a omega non-real, a non-zero real number. So our potential is just given by the standard harmonic oscillator. And the full Hamiltonian is given in 36. So we have a shift by up or down by essentially the absolute value of omega times a half. So if we have omega greater than 0, our h blows up as x goes to infinity. So this will give us a unique ground state in the fermionic part, and we should all know the energy spectrum of the harmonic oscillator, but now we shift it down by a half omega. So that's just going to be omega times n, where n starts at 0 and goes to infinity, while the spectrum in the bosonic part is the same, but we don't start at 0. We only start from 1. And for the other case, when omega is less than 0, we will have a bosonic part because h blows up to negative infinity. And we have essentially exactly the same spectrum, but we're swapping it and swapping the bosonic energies and the fermionic energies. But now obviously we'll see that it is positive, so we have the absolute value of omega, not just omega. So I just would like to get on to the Witten index. So before I can do that, we need to just know what traces are in quantum mechanics. So if we just consider an n by n matrix, and it has eigenvalues a sub 1 to a sub n, the trace is just simply the sum of these eigenvalues. These could be repeated eigenvalues. They could be the same, but no matter what, it's just the sum of these eigenvalues. So if we have an operator acting on a Hilbert space, and it has eigenvalues O sub n, and we have a complete set of orthonormal eigenvectors, we can write the trace as simply the sum of those eigenvalues, which is equivalent to taking the sandwiching it between the eigenvectors and summing over those. But it actually, we don't really even need to sum over the eigenvectors of the operator O. We can use the identity that the identity operator can be written in as this outer product sum of any orthonormal basis. So we can use that and just insert ones cleverly in our trace, and we will see that we end up essentially with a Kronecker delta over the K's and L's of phi sub L, and that basically gives us that in the end we are actually just taking the sandwich of O between phi any other basis. So we aren't limited to the eigenstates of the operator. So now the Witten index is defined as essentially almost like a graded partition function. So we are weighting the fermionic, well, we raise -1 to the fermionic operator. So on a bosonic state, that will give us a 1, and then fermionic state, that will give us a -1. And then we weight it with e to the minus beta h. And beta is just the inverse temperature. So now when we first, let's just consider the Hilbert space with positive, non-zero energy values. So our previous analysis tells us that each of these should come in pairs, right? So because of the degeneracy, and all of these will cancel because of one will come with a positive sign and the other one will come with a minus sign, the bosonic being the positive and the fermionic being the negative. So all of these energy states greater than 0 will end up canceling in the trace. And this is just due to the isomorphism between the two Hilbert spaces that we can use by using these fermionic raising and lowering operators. So so the fact that we actually had that beta h there is nothing but a regulator. So otherwise, we would essentially have a sum of -1 to the power n. If our energy spectrum is infinite, we'd have essentially the sum of -1 to the power n, which is formally divergent. You can change the ordering of in the sum to get whatever you want. So this Witten index is in fact independent of the inverse temperature beta, because we are only actually counting the energy equals to 0 energy states. So as I said, we reduced the index to just being a trace over the E equals 0 Hilbert space, and that just gives us the number of bosonic ground states minus the number of fermionic ground states. Or we can just write it as the dimensions of the Hilbert spaces, in terms of the dimensions of the Hilbert spaces. So it's actually very important, or a unique feature about these indices, like the Witten indices and its generalizations, is that if we introduce a parameter, our Hamiltonian depends on a parameter, say lambda, the index is actually independent on the value of that parameter. So I'm just kind of doing a little heuristic proof. There's a better one, but I doubt everybody knows path integrals here. So also, I should note that if one changes the value of lambda too drastically, so say one has a cubic potential and one sets that lambda to 0 and you get a quadratic potential, that will affect the Witten index. So it's within means of not deforming our Hamiltonian too much. So if we start off with the total number of n sub b plus n sub f states in our Hilbert space equals to 0, and this is at some arbitrary coupling value. And we vary the coupling to say tilde lambda. So we will now, it could alter the number of states, which I now just denote by the same variables with tildes on top of them. And we will have an overall change in bosonic states by delta NB and fermionic by delta NF. So our isomorphism between the two positive Hilbert spaces over there in 47 state that whenever we raise, if we have either we gain states in the ground state, or if we lose states from the ground state, so if they're lifted or dropped, these will always come in pairs. Otherwise, that isomorphism wouldn't hold anymore. We would have you wouldn't be able to pair everything properly. And so we see, because we're subtracting off the number of bosonic states from the number of fermionic states, this difference will cancel in the end, and you just get back to the original index. So essentially, the Witten index is independent of the coupling lambda. So this is very nice because this gives us the power of the index itself, is that, well, as I said, we do in perturbation theory, in quantum mechanics is hard when you start with that. There's a lot of systems that cannot be solved analytically, and we have to do that via perturbation theory. So if our parameter is small, we can apply perturbation theory, essentially doing a Taylor expansion in terms of it. And so, well, I can just continue is the stream still going? So as long as that's going, so I mean, I can just describe. So if we know we have an exactly solvable system, and then we perturb it by some interacting Hamiltonian, as I said, we can do an approximation in our couplings. But these approximations only hold when our coupling is very small. But if you have our coupling lambda being large, this kind of fails. You're summing larger, each term in your series is going larger and larger and larger, and hence contributes more to the approximation. So we can't just truncate our series and have accurate results. But now the Witten index says that we don't care about the coupling. So we can compute the Witten index for small values of the coupling, and then we can just ramp it up, and we'll still have a complete description, a very accurate description of our system through the Witten index. And if the projector comes on, I have given a little resource about computing the Witten index. Is it? So I think, once the slides come on, that's probably a good point to stop, because that's all I really have to say about the Witten index. And the next topic in my slides is very different, completely different. So if you do want to see more, I will show you my email address and I can send you the slides. or you can just come to me in 5:20 and we can have a discussion.
Your home address.
I don't feel comfortable giving it to you specifically. Everybody else can get that.
I'm being escorted to ask for your address.
Okay. Just waiting for the slides to turn on. But any questions while we wait? Oh, there we go. So yeah, there's a resource. So you just need to go on the archive and look up that paper number. And section 1 gives a very nice, very useful resource for computing the Witten index in terms of stuff called some exponentials, functions. I kind of just forgot. Okay. Dude. And so while we're waiting again, so I'm just going to write out my email because obviously, talk.
The least you could give me is a postal code.
That's tuxets.co.za. Okay, so yeah, if you have any questions or would like to see more of the slides, let me know. Yes.
So I'm assuming, like when you said that everything kind of exists in a pairwise state, like Fingerling and photonic.
Yes.
That's where the electrons.
Electron squarks.
Yes, all those
Photinos.
equivalents come from. What does supersymmetry say? Why don't we see them?
Oh, so the idea is that when one has a spontaneous symmetry breaking, it happens at a specific. So spontaneous symmetry breaking has a scale. Above that scale, the symmetry returns. You can still see it, but below that, it's not apparent. So that's exactly the reason why the Higgs mechanism at low energies decouples the electric and the weak forces. But once you go above an energy, they become one force. So, and the idea is with supersymmetry, the superpartners have masses at that cutoff range, and the hope is we pray that the energy level that the masses of those superpartners are at, or at least the lightest one, just hasn't been able to be probed by the LHC. So we're hoping for just one more larger collider, just one more. Give me a bigger circle, please. Or from CERN, or we could get a long linear collider from China. Those are probably the best hopes that we have at the moment for observing. Pardon?
The team collider.
I wouldn't trust the Timu collider, to be honest. Not to say anything bad about Timu, neither. But I don't really have any slides relating, so